window. How
Yeah,
about it?
absolutely. Absolutely.
Oh,
Perfectly
okay,
fine.
okay, okay. Thank you.
Yeah.
Okay. Right.
So I request Dr. Biswajit Das sir, please start the session.
Okay. Okay. We may start now. Uh, recording. Okay. Uh, Good evening to all. Good evening, Professor Otsuki sir, and all our participants. This is the AICT sponsored 6-day online ATAL FDP program. The title of the program is Advances in Material Science for Sustainable Development and Industrial Applications. And today is the second day, and today we have two sessions. Session 3 by Professor Joe Otsuki sir. He is from Neo University, Japan, and session 4 by Professor J. H. S. Jatana. He is from MNIT Jaipur. So now uh, I may request to our HOD sir, Dr. Dipankar Das, uh, to start the program.
Thank you, sir. Good evening, all, especially Honorable Speaker Professor Joe Otsuki sir, and respected participants from different institutions. So I just read out the short biography of Professor Joe Otsuki. Professor Dr. Joe Otsuki is a professor in the Department of Chemistry at the College of Science and Technology, Nihon University. He earned his Doctor of Engineering degree from the University of Tokyo in 1991. Following this, he served as a researcher at the Institute of Industrial Science, University of Tokyo from 1991 to 1999, and as a postdoctoral fellow at University Louis Pasteur, France in 1994. Since 1999, he has been a faculty member at Nihon University. Professor Otsuki has received numerous prestigious awards throughout his career, including recognition as a top peer reviewer in the chemistry and cross-field by Pavlons in 2019. The
ক্যামেরাটা অন করো
Solar Best Papers Awards from Elsevier in the same year, and the Pavlon Peer Review Award in 2018. He was also honored with ISPAC Lecture Award in 2017 and the Outstanding Reviewer Award for Material Chemistry Frontiers by the Royal Society of Chemistry in 2016. Earlier in his career, he received the Research Award from the College of Science and Technology and Nihon University in 2003 and the Special Lecture by Young Generation Award from the Chemical Society of Japan in 1998. With a strong academic background and extensive contributions to the field of chemistry, Professor Otsuki is highly regarded for his research commitment to advancing scientific knowledge. So, thank you, sir. So, over to Professor Joe Otsuki, sir. So, now you may go ahead, proceed, sir.
Thank you very much, Professor Das, for the kind introduction. And also, I'd like to extend my appreciation to the organizer of this online seminars. Today, I'd like to talk about the molecule-based materials and devices for a sustainable future and beyond. And I'm gonna share my slide. Is the slide all right?
Yes, sir. Yes, sir.
Okay,
Yeah,
so
absolutely. Perfect.
right, thank you. In this session, I'm a chemist, and the subtitle of this seminar is like in the materials science and technology for sustainable development and industrial applications. I'm not into industrial applications, so my talk will be rather into basic aspects from the point of view of chemistry for sustainable future. And my title include the term "and beyond." By that, I'm gonna tell you about future, not near future, but rather distant future. The chemistry today might play a role. So let me start. But however, before starting, I'd like to use one slide to introduce our College of Science and Technology. We have a graduate school, of course, and I'm I'm a head of graduate school affairs, so I like to advertise my graduate school, as I did in the CERTEC last week. The Nihon University is one of the largest private universities in Japan, and the College of Science Technology is one of the colleges, one of many colleges, and the Graduate School of Science and Technology is kind of the older brother of College of Science Technology, and the graduate school has 16 majors. Basically, we cover every aspect of engineering and science. Maybe we don't have a biology departments, but other than biology, we have basically all we cover all disciplines of science, natural sciences, and engineering. Let me use highlighter, laser pointer. Okay. And I work for the materials and applied chemistry major, and I'm in Tokyo now, and I'm commuting every day to the campus. We have two campuses, one in the middle of town and the other in the neighboring prefecture. So it's like a urban campus and suburban campus. So here is the graduate school application guidelines. If you have interested in joining us as a graduate school student and the doctoral course, just take a screenshot of this and check the website later. So here is the table of contents of my talk today, and this is not a strict table of content. My talk will be some kind of meandering things, but let me. Here is a kind of flow of my talk today. I'd like first to see about the world population and energy situations today, and then I'm going to talk about molecule-based solar cells, and after that, I'd like to give a brief overview of the nature's solar energy harvesting, that is photosynthesis, and I'd like to demonstrate how molecular organization is important in photosynthesis. Using examples of porphyrins, I'd like to introduce you our own works for porphyrin organizations. Some of the porphyrin organizations I already talked about last year in the CERTEC and the Indian Photobiology Society meeting. And then I'd like to introduce about the molecule-based catalysis. And then finally, I'd like to talk about the future direction of molecule-based devices. This part corresponds to this part and beyond. And then finishing off my talk with concluding remarks. So let me start with world population and energy. Here's the world population prospects. According to the United Nations World Population Prospects, and now it's 2025, so we are here, and the world population is still increasing. Of course, now the world's most populous countries, already India is number one, I think, and followed by China, United States, Indonesia, etc. Many of these countries are are Asian countries, and some are in Africa and South America, like that. So the population is still increasing. Now 8 billion people are living on the earth, and in 50 years is around here, 25, 75, so around here. Still 2 billion people increasing.
Hello.
On the other hand, Japanese population are decreasing. The Japanese population is shrinking now. We are here, it's 2025, and the shrinkage rate is kind of astonishing. So, and this trend is predicted to continue further, and so maybe the population will be halved in 100 years. Nonetheless, this is only a local thing, and the world population is still increasing. So energy demands is also increasing accordingly. And here is the world total energy supply by source means by a kind of energy. By source means the energy source. The energy production, which I think is equal to the energy consumption, increasing, and so the world population is still increasing, and the level of living standard will be increasing. So the energy demands will certainly be increasing, and so this is coal, and this is oil, and this is natural gas. So all are fossil fuels, and nuclear energy is producing a part of the total energy, but the natural energy is around here, and only accounting for a small fraction of the total energy. And so hydro energy, a kind of natural energy, on the biofuels and waste here, 9.4%, and the others, solar energy is included here. Not all of 2.2%, but some of 2.2%. So the total energy we are using right now is 6 times 10 to the 20th joule per year. But here it's other sources of energy is only accounting for a very tiny fraction of the total energy, but magnifying here, we see that nonetheless the solar energy production is increasing rapidly, according to you can see from here, and major increase is due to the Chinese production of solar energy, shown in the yellow color here. So the solar energy is 2.45 exajoule. And here is the total energy provided by the sun. Incoming solar energy is 5.5 times 10 to the 24 joule per year, and about half of that energy is reflected by the surface of the atmosphere, and reflected at the surface of the atmosphere. So 2.5 times 10 to the 24th. No, this is, sorry, remove this E, just 10 to the 24th joule per year is reflected. And the remaining one, which is on the surface, either on the land or on the surface of the sea, and then eventually it is reflected or emitted as a light, as a heat or infrared light. So this amount accounts for the 3.0 times 10 to the 24th joule per year, and about 0.1% of this energy reaching on the surface of the earth is fixed by photosynthesis. So the energy 3.0 times 10 to the 21st joule per year is now being fixed on the in the biological world. So in previous slides, I show that the energy human beings are using is 6 times 10 to the 20th joule. Then the incoming solar energy is due to the surface of this Earth is 10 to the 24th. So a simple division. By simple division, we can see that solar energy is huge, and humans only using tiny fraction of solar energy. The ratio is 1 to 10,000. So this means that in theory, if we can utilize only 1 in 10,000 solar energy, we can live. We can provide all energy we need. So the solar energy, solar cells are gonna be most important sustainable technologies for sure in the present and in near future. And this is the the famous graph showing the best research cell efficiencies published by National Renewable Energy Laboratories in the US. And I'd like to focus on molecule-based materials, molecule-based solar cells. And here, the magenta color indicates the cell efficiency of dye-sensitized solar cell, which was invented by Gretzel in Switzerland in 1991. this is but the efficiency is not almost steady, about 10%, and but this has a very important offspring. This technology is the basis for the now famous perovskite solar cells. I'm gonna tell you about the mechanism or structure of these cells in a minute. So the perovskite solar cells was invented by a Japanese researcher. The first one was not here, but first perovskite solar cell, the efficiency of the first reported perovskite solar cell was only about 4% or something, but the efficiency's been increasing very rapidly. And here in this, as indicated in this line by the blue line, and organic solar cells is also being researched actively, but the efficiencies were lower than the other solar cells. But recently, very good organic solar cells are being reported. Unfortunately, I'm not following this quite closely, so I like only to introduce you dye-sensitized solar cells and perovskite solar cells, which I am a little bit involved in the development. Here's the dye-sensitized solar cells cartoon. We have a thin layer of titanium oxide. This is a photo published by Gretzel for the first reported dye-sensitized solar cells. And on the surface of these nanoparticles are these ruthenium complexes. And the light is absorbed by this ruthenium complex. Electron is excited from the HOMO, the highest occupied molecular orbital, to its LUMO, the lowest unoccupied molecular orbital. And excited electron is quickly injected into the titanium dioxide layer. And so the oxidized ruthenium complex receives an electron from an iodide coming from, this is a solution, dissolving iodide ions. And then here are iodide ions, and giving electrons here and here. And as a triiodide, it goes back to another electrode and receiving an electron. So electron flow is from here via external circuit, maybe turning on a motor or a light, and then coming back to the other electrode. So this is the solar cell, dye-sensitized solar cells. And the perovskite solar cells is the structure or mechanism of perovskite solar cells is very similar to the dye-sensitized solar cells. And there is some titanium dioxide layer, the same as the dye-sensitized solar cells. And instead of, in place of organic or metal complex dyes absorbed on the surface of titanium dioxide, perovskite layer is used. Perovskite is a solid material having a structure like this one, the central cation surrounded by halogen anions, and then which are further surrounded by ammonium cations like this. This is only a portion of the solid material. This continues on and on, three-dimensional material. And then on top of it, a whole transport layer. This is a typical arrangement of there are some other arrangements, but this is a typical arrangement of the perovskite solar cells, and the whole transport layer is put on top of the perovskite layer, and then the other electrode is evaporated on the surface of the whole transport layer. And then light excites the perovskite, and the electron is injected into the titanium dioxide, and the hole produced is moved through the whole transport layer. The hole cannot go into titanium dioxide, but only hole is allowed to diffuse into the whole transport layer. And so the directionality is given by the unsymmetric arrangement of electron transport titanium dioxide and whole transport organic materials. Right, so the mechanism is very similar to the dye-sensitized solar cells. The initial perovskite solar cells was just the replacement of organic molecular dyes with these perovskite materials, and efficiencies was very low, but the improvement was very rapid. Improvement has been very rapid, and now its efficiency exceeds 25, around efficiencies reported are around 25%. So, and also these are flexible. These films can be grown on the flexible materials like polymers, and so Japanese companies. We'll have Expo 2025 maybe a few months away in Osaka. Kansai. This should be Osaka, Kansai, Japan, and this is a bus terminal of Expo venue, and the whole roof is now under construction, but all roof. The whole roof is covered by the perovskite solar cells, and I read on the website that the 257 panels will be used on top of the roof, each 2 meters by 1 meter wide. So it's a huge solar cell array, and the Japanese government announces that its target is perovskite solar cells to produce 20 gigawatt in 2040. And so in perovskite solar cells, the whole transport material, some of the whole transport materials inorganic, but some other solar cells organic materials are used, and the typical the most widely used whole transport material is this one. This cross-like carbon is called a spiral, and spiral methoxy. So spiral OMETAD. This is called a spiral OMETAD, but this has some problems, like this material needs additives, or this material is hard to produce, costly, etc. So the replacement for this material is under active investigation now, and we have also made some other possible alternative materials. So here are some of the examples. These structures are similar spiral thing, but the structure around here are somewhat different. And we tested our materials compared to spiral OMETAD. Spiral OMETAD. And spiral OMETAD. Here's a typical performance evaluating graph for solar cells, and in the x-axis indicates the voltage produced, and the vertical axis indicates the current produced. So current times voltage equals the power, and so the square, you can write square here or square here, and maximum area square is the power of the solar cell. So basically this curve is to the right or upwards is the better, indicates the better solar cells. And in this case, spiral or metad, it's a green line, so the performance is like here, and our material is less efficient. This is less efficient. Some of our materials are better than the spiral metad. And here's another evaluation method for the solar cells. And here's the wavelength of light, and for about 400 nanometer to 800 nanometer. In this range, in this range of light, we can see. So it's a visible light, and here are some ultraviolet, and here in the region of infrared region. So the vertical axis indicates the quantum yield of photon to light photon to electron conversion. So basically, they're very similar. Our material works fine, comparable to spiral or metad. And here is the cover of the paper we published using these one. Ryuji Kaneko was a PhD student at the time, and this is the actual solar cell, and this hand is of Kaneko's hand, and he's now working in a startup company producing perovskite solar cells. Start company was produced by a professor of Kyoto University in Japan. And I hope his company will grow, as well as the solar cell industries in general. And I'd like to talk about some of the molecular basis of how we can design molecular materials. Let's say that here's the aromatic molecular fragment, and let's say that we want to make an assembly so that the electron or energy transfer is smooth along the molecular stack, and then we can think about to attaching some intermolecular interaction sites such that this this dent and this what do you call these are complementary in shape, so we can spin coat or crystallize or drop cast them, and so that the molecule self-assembles into some ordered structure due to these intermolecular complementary interaction sites. So with these strategies, this is a very simple example of using that kind of strategy. Here is an amide group here and here, which is suitable for continuous hydrogen bonding, as shown here. NHO hydrogen bonding is repeated along these lines. And then with this hydrogen bonding, this part, this electron-rich aromatic part, is spontaneously align themselves into these one-dimensional arrays. so that this material is dissolved in a solvent, and then the solvent, after the solvent evaporated, material produces these fiber-like structures. So this is applied. This fragment is called TTF, tetrathiafluoride. Oh, sorry, this should be V, not B. This is an electron donor group, electron-rich group, and it's famous for organic conductor. So with this hydrogen bonding site, this organic conductor part is arranging themselves into a one-dimensional lines, as shown here. And so we applied this material as a whole transport material in the perovskite solar cells. And we found that conductivity is better than doped spirometad. So that we can avoid using dopant. Dopant is some disadvantage. The use of dopant has some disadvantages, like dopant is an ionic species, so that it attracts water, humid from atmosphere, and so that deteriorates the lifetime of durability or lifetime of the solar cells. And so we don't want to use the dopant if possible. So this is a very strong electron donor, so that dopant free, this material doesn't need dopant. And the VOC means the voltage, the maximum voltage in the solar cell evaluation graph here. And the VOC is better than this spirometad. But unfortunately, the maximum current is lower than the spirometad. So it's a rather challenging task to find better material than spirometad. But the dopant-free is a great advantage. Oh, so this is some cover reporting this results. So then I'd like to move on to the talk about the photosynthesis. This is, of course, the most important reaction on Earth, because all our lives depend on this reaction. In green plants, the carbon dioxide is converted using the energy of sunlight to produce organic compounds, carbohydrates, and with this reaction, the extra oxygen is discarded. But this kind of trash produced by green plants, but this is very important for other animals or other living things to live for their respiration. Of course, the plant itself need oxygen for respiration, and this is not only type of photosynthesis, but also there's photosynthetic bacteria as well, and some photosynthetic bacteria uses hydrogen sulfide instead of water as a electron source or reductant to reduce carbon dioxide, to fix the carbon dioxide as an organic material, carbon like sugar, and sulfur is produced in this case instead of oxygen. So how can these reaction possible? And I only show the initial steps. The initial step of photosynthesis by photosynthetic purple bacteria is carried out in a protein on the cell membrane. This is a protein structure solved by X-ray crystallography some years, quite a few years ago. And if we remove the polypeptide part of the proteins, we will see a beautiful array of molecules. And these are chlorophyll molecules made into a ring structure. One ring here, another ring here, and another ring here, the larger ring. And in this larger ring, there is a kind of tower, molecular tower, like this. And so let us see what happens in here. The sun is here, and light comes onto the reaction part, and then the energy, excited energy. One of the, this was too quick. One of the, this is a chlorophyll molecule, and one of the chlorophyll molecules excited energy is transferred to adjacent molecules, and then eventually goes into the center of this part. And this is a special, this is a chlorophyll pair, and which is called a special pair because it plays a special role. That is, now from here to here, what is transferred is energy. But from here, what is transferred becomes an electron. So electron is electron pops out from this molecular pair, the dimers, to another chlorophyll molecule and quinone molecule, and the lost electron is provided from another part of the molecule, producing a plus-minus charge separated state. So these are molecules used in this arrangement array, supramolecular array. Chlorophyll A, bacterial chlorophyll A, bacterial chlorophyll B, bacterial phyllophyton, and MC, and some other stuff. And so this marvelous structure, we are amazed and feel awe to these marvelous structures, and this structure, supramolecular structure, the molecular arrangement tells us that the molecular organization is very important for efficient energy transfer or electron transfer. So how molecules is organized? Everything, all materials, all living things, all inorganic things is made up of from atoms, and atoms arrange themselves into molecules or continuous structures. Molecules is defined as some entities that has a distinct size and shape, but other materials are continuous, like solid materials, metals, salts, and rocks. And I'm interested in the molecular species, molecular entities. In biology, we find amino acids, fats, and carbohydrates. These are essential molecules. And molecules assembled just what we saw in the photosynthetic reaction center as an example. It assembles into a larger supramolecular structures like protein assemblies or cell membranes are the molecular assemblies. And also it binds together to make polymers like proteins, amino acids binds to produce proteins, and DNAs and RNAs are polymers that incorporate information, genetic informations, and these are further assembled into cells, which further assemble into organs, which further assemble into living organisms. And for that matter, these living organisms, like us, assemble into societies, and many societies, many biological species constitutes a biosphere on Earth. So from point of view of chemists, we are interested in how this molecule can be assembled into higher order structures like supramolecules or polymers. So in this case, intermolecular interactions are key to organize molecules. We notice this concept. This concept is powerfully advertised by Jean-Marie Lehn. This is his famous book of supramolecular chemistry. And supramolecular chemistry, these are quote from this book. And supramolecular chemistry may be defined as chemistry beyond the molecule. And just as this is a nice demonstration of supramolecular chemistry. Just as there is a field of molecular chemistry based on the covalent bond, there is a field of supramolecular chemistry, the chemistry of molecular assemblies and of the intermolecular bond. And this is more concise version. Supramolecules. Recently we use the term supramolecules, but in his original book, he called the assembled molecular assemblies as not supramolecules, but supramolecules. So supramolecules are two molecules and the intermolecular bond. What molecules are two atoms and the covalent bond? And this is a nice one. The supramolecular chemistry is a sort of molecular sociology. So what are intermolecular interactions? This is a basic chemistry. Covalent bonds is, this is an intramolecular interaction. Atoms combine with covalent bonds to produce molecules. And the molecules can further bind to another molecule by using intermolecular interactions. Coordination bonds is one of them. This is somewhat borderline between intramolecular bonding and intermolecular bonding, depending on the context. Hydrogen bonds are intermolecular. The most typical intermolecular interactions, strong intermolecular interactions, however, much weaker than the covalent bonds, but stronger than other intermolecular interactions, such as van der Waals interactions. This is just the attractive force between neutral molecules like this. So what we want to do is to incorporate these intermolecular binding sites into molecule and design a molecule such that that molecule will be assembled themselves into higher order structures that have properties that we want. I've been using porphyrin molecules quite some time, so let me just briefly introduce you the properties of porphyrins. This is a basic structure of tetraphenyl porphyrin, and here are molecular orbitals and HOMO orbitals and LUMO orbitals, and absorption absorption corresponds to the excitation of HOMO electron into LUMO electrons, and the quantum mechanical interaction between different absorption leads to a larger absorption and smaller absorption. So these absorption is just from the almost all coincides with the visible light, and so this is a very strongly colored material like purple or green or something like that, and nice for this would make it qualified as a nice photosensitizer, and these electron can be taken out from the molecule, or electron can put into the molecule. So this is shown by these. This is a graph called a cyclic photomegram that investigates the electrons coming in and out of the molecule. And so you can put one electron, two electron into this pi electron system, and you can remove one electron and two electron from this pi electron systems. So basically, it absorbs very nicely the visible light and also UV light, and then electron can be transferred from one porphyrin molecule to another molecule, and so this is very functional molecule. Oh, and also, good thing about porphyrin is we can synthesize porphyrins and decorate them with various functional groups like these, and also we can put various metal ions at the center of the porphyrin ring, and if you put zinc ion here, this metal accepts another coordinating group, another ligands, like to produce these types of structure. And so you can choose from various ligands, and you can put various intermolecular interaction sites on the peripheral sites of porphyrin, like these hydrogen bonding, electrostatic interaction sites, metal coordination sites, and the hydrocarbons. And if you combine these two, you can even put coordination sites on the peripheral site of zinc porphyrin. In this case, porphyrin itself assembles into higher order structures. Some of them I'll tell you about soon. This is an example of a hydrogen bonding assembly of porphyrins. And here we introduce a medinium group and carboxylate group here and here. And we put zinc ions here into the surrounding porphyrins, but not at the center. And so that the pi electron energy level is going to be different. And this has a higher energy, this has a lower energy. So on excitation, energy transfer happens from the peripheral site to the center. And so this mimics an aspect of light harvesting center we have seen in the purple bacteria photosynthetic reaction center. And this is shown by time resolved fluorescence measurements. So actually, efficient energy transfer happens from here to here. And these intermolecular binding can be seen. We can actually see how these molecules are assembled into higher order structures by using a scanning tunneling microscope. We put a long hydrocarbon chain around the porphyrin framework, and then these porphyrins are adsorbed on the surface of graphite, a special graphite, which is atomically flat, and so that we can observe one molecule by one molecule by using the scanning tunneling microscope. And if we put a special intermolecular binding sites here and here, so in this case, hydrocarbon part interdigitates to produce a nice array of porphyrin molecules on the surface. And then if we put additional intermolecular binding sites here, here we have introduced a carboxyl group here for intermolecular hydrogen bonding. Then we see a double row structures like this. So we actually can make these molecules assemble themselves into a predisposed, pre-planned, predicted manner. And this is just an interesting thing for this molecule. The one we have just used, the amidinium group here, for light emitting diode device. Group of researchers in Greece have shown interest in our material, and we have prepared this molecule again and send them, and they put as a layer of light emitting diode. And if they use this layer, the luminance, I think it's the brightness of the device is increased significantly compared to the one without the layer, and so that this material may find applications in this area as well. Well, just as I explained, if we put a coordinating site ligands here, and we can have this type of porphyrin assemblies. And we have prepared this one and this one. This is actually a chlorophyll molecule and modified chemically by the organic synthesis techniques. And we also put a fluorine here. This is some good electron acceptor, and we mix them together in a 3:1 ratio. And so we have we don't have control over the combination of these two, so they mix randomly to produce various types of these tetrameric structures, like this one, like these, containing a various number of fluorine groups in the assembly. But one of them is this one, and this is light harvesting model I have explained, and I think I have, yeah. And in these complexes, we have done various spectroscopic studies, and then found that the energy transfer happens in 3.8 picoseconds, time constant, and electron transfer also happens in 3.8 picosecond time constant, and the excited state lifetime is 4.3 nanoseconds. And so basically, much before deactivating, the energy transfer happens very quickly, and followed by electron transfer. So one of the chlorophyll molecule absorbs light, energy transfer followed by electron transfer. These processes happens basically 100% quantum yield, and so this is another mimic of a photosynthesis reaction center. And here's another version. We have put a tyrosine group here. Instead of fluorine, just opposite to the fluorine, tyrosine is a good electron donor. So upon excitation of porphyrin sensitizer, electron transfer occurs from tyrosine to porphyrin. And so we have mixed these two. Oh, sorry, this is 1 and this is 3. And mix these two, the one with tyrosine and without tyrosine. So we have these assemblies randomly containing various number of tyrosine group. But this one, let us focus on this one. This one has one tyrosine group, and the energy transfer happens around here, and electron transfer follows. This is another type of photosynthesis initial step model. In this case, what is interesting is by introducing tyrosine group, the energy level of this porphyrin is lower than the energy level of these two. And so energy transfer happens from here to here, here to here, but not the other way around. So the energy transfer is only one way, which is favorable because electron transfer happens here. And there is no reverse electron transfer, reverse unfavorable energy transfer is involved. So this is confirmed by some spectroscopies. So basically, this is like an energy funnel. Energy flows only towards the reaction center, but not the other way around. So now let's move on to the catalysis. The catalysis is very important for the to make the reaction possible, make the reaction easier, make reactions with less energy. So there are mainly two types of catalysis. One is heterogeneous catalysis, and the other is a homogeneous catalysis. And this is I think this is the major one, like solid. But for electrochemical catalysis, this is a solid surface, or for photocatalysis, semiconductor particles or colloids are used. And on the other hand, the homogeneous catalysis is used for organic synthesis mainly, but for energy-related area, this is rather minor, but this has some advantages. By molecular homogeneous catalysis, detailed mechanistic probe possible by using various spectroscopic techniques. And also a good thing about molecules or homogeneous catalysts is a tuning with atomic precision by a synthetic modification, systematic modification, systematic studies are possible. So the important energy-related reactions include water lysis to produce hydrogen and oxygen, or oxygen reduction. This is important for fuel cells. And also, this is, of course, important reaction, the reduction of carbon dioxide. And catalysis field is very vast, and I only speak about a very tiny specialized part of the catalysis. Today, I'd like to tell you about how the molecular organization plays, what molecular organization plays in catalysis. And also, I'd like to limit my talk on the porphyrin dimer. Porphyrin dimer, how the porphyrin dimer behaves compared to porphyrin monomer in terms of catalysis. So this is reported in 2015. This is a dimer of iron porphyrin, and the bridge part is modified. For the bridge part, also benzene or metabenzene were used, and FETPP is a monomer of this one. So they compare the electrochemical catalysis performance for carbon dioxide to reduction of carbon dioxide to carbon monoxide, and relative catalytic current was compared. So the monomer porphyrin only have a 1.5. This doesn't have units because these are just relative values. And metadimer gives a value of 35, so a very great improvement, but also dimer is much better than that. So this demonstrates that the dimerization is very effective to improve the catalysis performance, and also the relative distance or structure of the dimer is also very important. And this is a classical work. The cobalt porphyrins. Cobalt porphyrin dimer was prepared by Coleman many years ago, and this is an early study that shows the molecular organization is very important for catalysis. They investigated the oxygen reduction reactions. So oxygen reduction, if you reduce 4 electron reduction, you get H2O, but if you do 2 electron reduction, you get a hydrogen peroxide. So the selectivity of these catalysts are important, and this is the selectivity of producing a hydrogen peroxide, and this is a current. So for monomer, percent H2O2 is 69%, very high, and the current is 0.4. And for this dimer, H2O2% is about 70%, and the current is about the same as the monomer. So there is a little dimerization effect, but this dimer very similar to this one, but a slight difference in the bridge part. The number of carbon atoms here and here are different, and then dramatical effect was observed. Percent H2O2 is less than 1%, which means more than 99% of the reaction results in the production of H2O, not the H2O2, and the current also increases. So again, the dimerization is effect, but the structure of dimer is also important. Now, this is more recent one published in 2021 by the group of Cook in the USA, and they produced a dimer like using the coordination interactions for these bridges and investigated the oxygen reduction reaction of these molecules, and they observed again dramatic increase of selectivity and as well as the catalysis performance. This is a monomer. H2O2 2% is 50%, so random production of H2O and H2O2. But upon dimerization, the percent hydrogen peroxide reduces dramatically, meaning that they are more selective towards the water, and that the reaction rate increases dramatically for the monomer 9 times 10 to the 0th per this unit, but dimer has about 10 to the 4th or 10 to the 5th times faster reaction was observed by using these dimer structures. So this is a recent work, and so this is still a very topical subject. Why the dimer is efficient? Some researchers proposed a mechanism of the dimer, but basically, I won't go into details, but basically, the dimer structure has a special environment for the substrate. If you attach water molecule, oxygen molecule is coordinated here. There is another coordination site very close to the one that coordinated, so that these bridge structures can be formed, and then the reaction pathway is affected dramatically compared to the monomeric structures. That's the reason for higher selectivity towards a certain reactions. Why I talked about the porphyrin dimer is because we have recently were successful in producing porphyrin dimer structures, which we will explore the possibility of application in catalysis. So let me talk about our porphyrin dimers a little bit. And this is a molecule we have designed and prepared, and the three-dimensional structure is like this one. This bond is twisted and this bond is twisted, so it's like this one. And so we put metal ions on this molecule, and then the coordination happens here, 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 and here, 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 so resulting in this dimer structure. So this was our intention, and indeed we have shown that upon addition of zinc ion here, the absorption spectrum shows a very nice blue shift from here to here, indicating that these high electron systems, porphyrin is arranged in a face-to-face manner like this one. What is interesting is that the dependence of zinc ion concentration is not a simple binding curve like typical binding curve like this, but it shows a pronounced S-shaped curve. This indicates that the binding process is very synergistic or cooperative, and in the less ion concentrations, the binding is lower, but after some ion concentration, binding is stronger. So this is an interesting phenomena, which is known for as the allosteric effect, which is observed in hemoglobin in our blood cells, so that the oxygen transport from our lung to the terminal part of our body can be efficient. So this allosteric effect can be reproduced by an artificial setting like this one. We have analyzed NMR very closely to predict the solution structure like this dimer, as we expected, as we hoped for. And we finally got the crystal structure, and crystal structure demonstrates actually we have these dimer structure like this one. So here's the cover for the paper. This is these are Japanese letters, and I wrote porphyrin dimer, which is a Japanese way of pronouncing porphyrin dimer. And now we have this one in our hand. This molecule is relatively easy to prepare, so we can have certain amount of this material, and the dimerization is very simple. Just mixing with zinc iron is enough to produce these dimer structures. And so we are now working on putting other metal ions like cobalt or iron that we have seen that have catalytic abilities. So we put those metal ions here and here and investigate the catalytic abilities for energy-related important reactions, in addition to other projects. And maybe a remaining of 5 to 10 minutes, I'd like to talk about this part and beyond. So these topics I have talked about can be applied in the near future, like solar cells and catalysis. It's a kind of extension of the present state of technologies. But on the other hand, completely new way of using molecules as the molecular devices is also very interesting, even though it may not be applied in the immediate future. If it can be applied, it will be a very long, distant future, but the phenomena or development of these molecular devices is a very interesting from a basic point of view of chemistry. And this is a picture of a certain meeting. And here is Professor Savage, here's Professor Lane, Professor Firinga, and here's Professor Stoddard. And he got, I introduced him a few minutes in his talk. He got a Nobel Prize in Chemistry in 1987 by the work of supramolecular chemistry. And Firinga, Stoddard, and Savage got Nobel Prize in Chemistry in 2016. And here's me. And the Savage, Firinga, and Stoddard got a Nobel Prize by the work of their molecular machines. And this is Savage's molecule. This is axle, and the ring is this molecule composed of axle and the ring. And by putting metal ions here, these two can be extend or shrink. So they call this molecule, this supramolecule, like a molecular muscle. And this is also an axle and ring structure. And there are two stations. And so these moves from here to here and here to here. So it's go and back and go to and fro. And so this is kind of molecular shuttle. And this is prepared by Firinga. And this looks like a very simple molecule, but very ingeniously designed molecule such that they here's the double bond here. So double bond is well known for isomerize cis and they undergo cis and trans isomerization. But what was special about this molecule is by the steric hindrance here and here, the thermal change from here to here only occurs in a certain direction, not certain direction of rotation. And then light is shined from here to here. There is only possible, it's only possible to rotate in one direction, but not the other. So that they realized one-way rotation using molecules. So, and they call it a molecular motor. So this is from our lab, and molecular rotor can be visualized. Actually, this is the image of scanning tunneling microscope. In this molecule, it shows this a single molecule, and this is orienting to the left, this orienting to up, this orients to left, and then after that, this is oriented towards the right. And this turns around, after maybe 1 minute, this turns the other way, and this is going up, this is going left, and this is going up. So this molecule change the orientation from here to here. So we can actually look at how molecule change rotation. And this is a very simple molecular toy. And we put a simple zinc tetraphenylporphyrin and a ligand which quenches the fluorescence of zinc porphyrin. And so this is not emitting. This is in the off state. But if we add a proton, make the solution acidic, the proton attaches to the pyridine group so that these two molecules are separated, and then it fluoresces nicely. Or if we put an electron, this is a good electron acceptor. That's the reason why this zinc porphyrin doesn't emit. But we put electron here. Now this zinc porphyrin can fluoresce. So this is in the on state. So this is the world's tiniest light switch, like this one. This one can be made only by these two small, tiny molecular components. And this is another example of a molecular switch we have developed a long time ago. And if we light is absorbed from here, nothing happens because this group quenches the energy. But if you reduce one electron, reduce this part, you can do it. And then the light comes here, energy transfer then happens from here to here, and the light is emitted from here to here. So this is, these should be reversed. This is off state. So this this one should be here, and this one should be here. So this is the world tiniest switch for energy transfer. So these types of things can be developed into these types of things is very nice, but the problem is we don't know how to make them integrate into a meaningful devices. So we now don't know how to use it, but we can. So the question is, how far can we go with molecules? But thing is, the living things, we are made of molecules, and we can know by looking at the nature, looking at biology, we can know that molecules can do marvelous, very sophisticated things. So this is another citation from the Jean-Marie Lane's book, The Chemist Finds Illustration, Inspiration, Stimulation in Natural Processes, as well as confidence and reassurance. This is the one I want to stress, since they are proof that such highly complex systems can indeed be achievable on the basis of molecular components. This is a summary of my today's talk. Just briefly tapping it again. Solar energy harvesting is key to meeting the world's growing energy demand. And the molecule-based solar cells offer promising new technology, among other technologies. And the molecular organization is crucial in natural solar energy harvesting, that is photosynthesis. But the molecular organization is crucial in all biological processes, as a matter of fact, for that matter. And using molecular organization, artificial photosynthesis models can be made by learning from nature, and catalysts are necessary to make reactions more efficient, make the reaction with lower energy. Again, for catalysis also, for molecular catalysts, molecular organization is vital, which is shown by the dimer of porphins. And in the distant future, development of molecular level devices can be envisaged, although at the present stage, we don't know how to integrate them into commercial product. But anyways, opportunities are wide open, I think, which we can see. We can get proof by looking at nature, how a molecule can do wonderful things. So the molecular opportunity is only limited by the laws of physics. We can't violate the laws of physics, and but also it's only limited by our imagination. So I'd like to thank my students and collaborators that made the works I introduced you possible. And for funding, I appreciate various organizations, but particularly I'd like to appreciate Kakenhi from the Japanese government. And many thanks for your kind attention. Oh, I can't read this. Okay, so I think that's it.
So thank you very much, sir, for your honorable session. So now I'd like to request our respective participants. So you have any questions, so I directly ask the question, or you can write in the mass chat box your question. So this is the interaction session.
Yeah, I have a question. Can you hear me, Professor?
Yes.
Yes, sir, you are.
Yeah, in one of the slides you have shown organic conducting polymers like P dot. I want to know what is the thermal stability of organic conducting polymers, and what about the efficiency of those solar cells if you have worked in that field?
Hey, this is still shared.
Yeah, in one of the slides you have shown P dot, polyethylene terephthalate thiophene.
E dot.
Yeah.
E dot. I'm not sure. maybe this one. No, I don't think I have used P dot.
In one of the slides you have shown, it's fine, no issues. According to you, how is the stability of the organic conducting polymers?
I haven't used polymers. I only have used the small molecule organic conductors.
Okay.
And for these small molecule organic conductors, the stability have been checked, and some of them are better than spiral ormetad, which is a benchmark organic conductors for which is used for perovskite solar cells. And some are bad, but in general, the stability is better than spiral ormetad.
You mean thermal stability?
Yeah.
Okay. Okay, thank you.
Okay, thank you.
Thank you, sir. So anybody, please raise your hand or post your question in the chat box, or you can directly ask question Professor Joe Otsuki, sir. Any participants? So Vishwajit Kundu, sir, you can ask.
Hello.
Yes, sir, you are audible, sir.
Okay.
Vishwajit Kundu, sir.
So yes, sir. So my question is, sir, in your presentation you have mentioned a STM image. So what is the temperature of this image actually? The image
What's
you
the
have extra temperature. That means measurement temperature. The measurement performed at room temperature.
which one? Yeah.
At some room temperature. STM image.
Yeah, temperature. In what system you're mentioning?
So
Which system?
go to your
you're mentioning?
image slide. That means in which you present some STM image of some organic molecule.
STM. Yeah. It's a room temperature.
Yes.
Room
Yes,
temperature.
room temperature.
Room temperature.
Okay.
Yeah,
Okay.
room temperature and solid liquid interface.
Okay, solid liquid interface at room temperature.
Mhm.
Okay.
In atmosphere. Yeah.
Okay. Thank you.
Okay.
Anybody? Any participant? Do you have any question?
Shoma Mukherjee,
Yes.
Shoma Mukherjee actually asked one question to that among the different type of solar cells, you have mentioned which one will be more effective for environmental success.
Sir, actually question is given in the chat box. Among the different types of solar cell, you have mentioned which one will be more effective for environment sustainability. The question coming from Shoma Mukherjee.
Okay. Which is most effective in environmental sustainability? Wow. It's difficult. I think we have just prepared some organic materials and tested in the laboratory scale, and for real environmental sustainability, we have to check all production stages to durability. So I cannot say which one's the most efficient, the best for environmental sustainability. We have to take into account the for example, organic solvents used for the synthesis, etc. And so, sorry, I don't have the answer right now. For just the efficiency of efficiency for solar cells, I can tell we have numbers for specific numbers, but for environmental sustainability, it's a difficult question.
Okay, thank you, sir. So, any question from participants? Any more question? Okay. So, I hope there is no questions from the participants. So now, thank you very much, sir, for your
Thank you.
wonderful lectures. And I would like to call upon Dr. Vishwajit Das to share digital memento. Sir, we have a digital memento as the program is going on the digital platform. So, as a small token of appreciations from the Dr. Sudhir Chandrasur Institute of Technology and Sports Complex, JS Group. So now we are sharing a digital memento for a small token of appreciations. Kindly accept it. So I'd like to request Dr. Vishwajit Das, kindly share it.
Okay. Before that, sir, pardon me. Actually, Krishnan Gopal raised his hand. Actually, if maybe he has some question. So, is any question from Krishnan Gopal? You raise your hand, Krishnan Gopal, sir. Okay. So, if not, then so, sir, once again, thank you so much for accepting our invitation. And due to the time gap in different countries, and at the moment in your country it is very late night. So, and still now you have with us to share this wonderful lecture and your experience, the vast experience with us, and enrich us over this molecular chemistry and the application of them in different sectors, particularly in energy. And the work you have shown, the wonderful work, and the Nobel laureates, introduced the Nobel laureate and their work with us. So we are very much happy and we are very much honored that you, with your busy schedule, you give us this opportunity and share this. So, so before sharing, so I am requesting you just to, if you just close your presentation, so I am just present my memento, sir.
Mm.
Sir, if you just stop your presentation, so I will now present now the token of appreciation digital memento.
Okay. Oh, I say something.
Yeah, sure, sir, sure.
Oh, thank you very much. Oh, yeah, this is this. First, I was invited about this this program. I was not sure because it says the faculty development something, and so I was wondering what were different from normal conferences and the faculty development one. But so I tried to not go into chemical details. So I try to make my talk general as much as possible, as much as I can. So I hope my attempts were successful. and thank you very much for this opportunity. I greatly appreciate it. Thank you. I think that's all I have to say.
Sir, he is asking you to close the presentation slide.
Oh, I mean, yeah. Okay. Close my slide. Okay. Okay.
I would like
Yeah,
to
yeah, yeah.
yes,
So that
yes.
you can show the memento. Yeah. Stop sharing. Yeah. Sorry.
Yeah.
Sorry.
And this is the moment. So I would like to request all the participants. So if you can open your camera, and this is the moment we'll take a digital photograph for all of us. This moment, share this moment. And thank you, please, sir. We would like to request, please accept this small token of appreciation from our side, and for this wonderful, wonderful lecture you have presented and shared this knowledge to us actually. And hope we'll meet and share and work together in future.
So sorry for interruption. Biswajit Kundu has raised a hand. Sir, do you have any question? Biswajit Kundu, sir.
Yes.
No. That
Okay. 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 Thank you. Thank you, sir.
ঠিকই আছে বলো তখন তো লাভ হয়
Okay.
আমরা
Thank
সাতটাও
you.
দাঁড়িয়ে
Thank
পড়েছিলাম
you so much, sir.
মিথ্যা কথা বললাম তুমি ঝাবড়া হয়ে বসে
Thank you.
Thank you, sir.
আমরা সাতটাও তো দাঁড়িয়ে পড়েছিলাম আমি তো ওরা কোনো দোষ করতে
So
চাই
may I
সব
leave?
দোষ বড়েরাই করে এটাই ঠিক
Yes, sir.
Sure, because
Yeah.
already it was very late
Yeah.
night actually.
Yeah.
So
So
yeah, definitely,
ha- ha-
definitely, sir, and have a good night,
yeah.
sir.
Have another lecture and a good night. Thank you.
Yeah,
So
thank you
I
so much, sir.
hope to see you again.
Yeah, sure, definitely.
Okay.
Thank you, sir.
Bye for
Good night,
now.
sir. Good night.
Good night.
Good night, sir. So now the participant, uh, I'd like to mention that so this is now we entering the day 2 session 4, which is by Professor H.S. Jatana sir, and he will give a lecture on semiconductor manufacturing from specification to production product. So just few minutes we want to take. If sir is already with us, or I will check that. Uh, Professor Harpreet Singh Jatna sir, sir, are you with us?
Yes, I am there.
Oh, yeah. Good evening, sir. Good
Yeah,
evening,
good
sir.
evening, good evening.
Uh, Thank you for accepting our invitation. And this is, we know that this is very late night, or this is a night in this, but this is the AICT rules that we need to make this online faculty development program in this during this time session. So we apologize for this inconvenience actually, sir. And now to introduce sir, I would like to request Dr. Dipankar Das, the HOD of Basic Science and Humanities Department, Dr. Subir Chandrasur, Institute of Technology and Sports Complex, sir. Please introduce sir to our participants so we can proceed. Dr.
Okay, thank you,
Dipankar, sir.
Biswajit, sir. Thank you, sir. Good. I just read out the short biodata of Professor Engineering Education from British Philharmonic, USA. for some time where he worked on designing 6502 microprocessor, later joined ISRO. He has more than 37 years of hands-on experience in various domains of semiconductor like VIZ, VLSI design, CMOS process development and integrations, IC test and characterization and semiconductor manufacturing. As group head, he led a team of 85 scientists who developed 85 VLSI products for space technology and application, and few process technology like SOI, MOSFET, BICMOS, OTP, MTP, HV, etc. He is a professor at so you may go ahead, sir.
Okay, so is the screen visible?
Yeah.
Yes, sir.
But if you make it presentation mode, yeah, absolutely fine, sir. It is perfectly visible.
Okay. So I have chosen this
Thank
topic
you,
because
sir.
as you are aware that 2 years back the government of India they came out with a semiconductor policy 2021 for giving an impotence to semiconductor manufacturing in India. At present, we have only one fab, which is at SCL Semiconductor Lab. It's not a commercial fab. It's a very limited capacity, 1,000 wafer starts per month. So here in this presentation, because I have around 75 minutes, I can only give you an overview of that. What are the verticals and what is the present status in India? Okay, so we have scenario all of you. We have a huge requirement of various electronic devices. All these devices they need semiconductor chip, mobile set, laptops, set-top boxes, and energy meters. A lot of devices are required in defense, space, atomic energy, railways, etc. All sort of electronic devices. If you see the market-wise, presently our market of electronic system in India is close to 64 billion by 2026 and 110 billion, close to $100 billion by 2030. It's a huge market. This is the head of different categories like wireless communication, consumer, automotive is again picking up with the electric vehicles, 22 billion kind of thing, wireless communication and things like that. So it's a huge demand, and right now we are not making anything in India. We are all importing semiconductor devices. We are doing only assembly, which is a very, you can say, a low value addition job. It's not a high tech job. So this is the semiconductor market if you share by application side. And if you see 2025, we have this portion smartphone, then consumer, then industrial. But if we have to start today making semiconductor chips here, there are certain segments which is very, very difficult to enter. In the sense, we don't have the technology, frankly speaking. For example, smartphone, we cannot design a high-end processor here. We cannot design and manufacturing hard the top-end processors as well as the memory. So this is ruled out to begin with. Consumer electronics, industrial electronics, yes, we can do, but we cannot do about personal computing, servers, automotive, we can do. And to some extent, we can do for wireless. So this is the scenario. And as you are aware, only now there is a risk of use when we use semiconductor chip which are fabricated outside. So these things there are security concern. There is a during the COVID supply chain was disrupted. There is economic impact and some control issues. So I will not go into all these details. a fab, semiconductor fab or a foundry where these semiconductor chips are made. Why a commercial fab didn't come in the last 40, 50 years, the last 30 years, you can say, because this CMOS started in around 82, 83, so close to 30 years. So we had the first fab in 83, which was at 5 micron that time. The prevailing node was also 5 micron, 4-inch wafers. But after that, we couldn't make any commercial fab. The reasons are given here. The cost is huge. We don't have the technology, and it's not only the fab cost. There is a operating expenses are very high because there are more than 350 gases and chemicals which you have to maintain. These gases and chemicals, they are not made in India. You have to import. They are ultra pure. Huge requirement of power, huge requirement of water. And then you need your own design IPs. What to make in those fabs. You need design IPs. That also we don't have. So in the last 2-3 years, as you might be aware of the China-Taiwan geopolitics, because 70% of the semiconductor manufacturing is based in Taiwan. And that is the reason China showing military muscle to them, and US. In fact, when in early 80s, when this CMOS revolution started, most of the production was in US, but finally it got shifted outside the US, though most of the R&D is still done in US. So US also has a very ambiguous program, very ambitious program. They are putting $52 billion in subsidies for semiconductor manufacturing. India is putting around $10 billion. The European Chips Act, they are putting 43 billion euros and like that. So South Korea is also putting huge amount. Samsung, as you are aware, it's a South Korean company doing well. China is also picking up. So in India, we under MITI, under Indian Semiconductor Mission, these are the 3 schemes: PLI, DLI, and manufacturing, giving subsidy to the manufacturing units. Besides, there is a C2S program where we are working with 110 academic institutions where design tools have been given, and support to fabricate their chips in outside foundry is also been given, besides manpower support and like that. So these are few of the units which have been cleared so far. And fab is only one, which is a Tata fab. And all these units, as you can see, they are all in Gujarat, except one with Tata Electronics assembly is in Jagi Road, Assam. And these are the investment which are planned. These units, some of these units, their civil works are in progress. Maybe in the next 2 to 3 years, the equipment installation will begin, and maybe they will run in production after in 2027 and 28 kind of thing. These are the locations of these units. This is C2S. As I told you, 110 various universities are involved, where government has given them the support, manpower in terms of SRF, JRF, then EDA tools, which are quite expensive, and then fabrication support in outside foundry. Now, let's when we talk of a semiconductor ecosystem, there are a few terms which are used. IDM, like we call it, integrated device manufacturer, like Intel, which do everything, like they design and they make their own product. Foundries, they will not make their design, they will produce for others. Like TSMC is a foundry, UMC is a foundry, global foundries, and there are many other. Tower Charge is also a foundry. And fabless design, there are many companies who don't have manufacturing basis, and they only do the product design or chip design, and they go to TSMC for fabrication. For test and packaging, they will go to somewhere else, but they don't have their own manufacturing basis. Example is Apple. Apple is a more than I think 15 or 16 billion dollar turnover, and they don't have any manufacturing line, but they design their own chips and own products, and they make the product also, and all their chips are being done at TSMC, which is a Taiwan Semiconductor Manufacturing. Then there is an ATMP, which is basically a packaging and assembly, and offset is also same, which is once you get the wafer, you go for a wafer sorting, testing, and packaging, and then final device testing, reliability, and QA analysis. So these are the various, you can say, the nomenclature about the semiconductor ecosystem. Then the various verticals. We have a process technology. Process technology means the process engineers, they will develop the technology, how to develop the components, like how to make a transistor. Transistor are of many times, different types. BJT is there, CMOS is there, NMOS, PMOS, different voltages, different VTs. So there are more than 100 different types of transistors, and they will design that and how they have to be made, because the process of making the transistor is a purely chemistry and mechanical engineering. So you see, one should have a good knowledge of thermodynamics also, because the wafers see temperature as high as 1200 degrees. So one should have a knowledge of mechanical, like stresses are developed and things like that. And of course, chemistry is basically a chemical reaction, but the end result is a electrical one. So the process people, they design these components, and since we don't have any fab in India, we don't have any process engineer expertise available in India. And then there is a design technology. Design people, it's a integrated circuit design, which means they will take these components and they will design circuits like memories, processors, A to D, D to A, whatever. They will design circuits based on that. And the process engineers, they will give certain information which they require, which is necessary to be able to design circuits, like the information about the components, the characteristics, the VA curves, how to lay out those components. All those information is available in PDK. PDK means process design kit. So in that, one has to study and whatever relevant information of process which is needed for a design engineers, that are available, and how those VTs change with temperature, and think about matching information. All that information is given in the PDK. Then there are a lot of fab utilities. I will go through this quickly to show you different type of gases, chemicals are used, and they have to be in ultra pure. And then there is a fab manufacturing technology where these ICs are made, and it has to be run continuously 24x7. And then your clean classrooms have to be maintained at a particular level. So all those things comes in the manufacturing, which we call it a fab or a foundry. Then once the wafers are out, they go to for wafer sorting, then testing, assembly, and things like that. So there are various kind of, you can say, verticals in this particular industry, and you need a lot of manpower, each specializing in its own field. And waste management is also, because we are playing with phosphine, arsine, tungsten, hexafluoride, very, very dangerous chemical. And so after that, you have to handle this waste also. Okay, so this is, if you see a very manufacturing flow, there is a design. There are a lot of steps in a design, as you can see. So synthesis, verification, this whole thing is, design is there are various steps, particularly in a digital design. It's a lot of tool dependent. There are a lot of steps in that. And after that, it goes for you have to make the mask. And after mask, it goes to the masks go to the wafer fab for fabrication, then it go for testing and packaging, etc. And then system integration, the product is made. The chip goes in some system and the final product is made. So this is the complete flow of that. So PDK is an important link between the process and the design. It gives all information related to the design which a designer needs, the information related to the process, how that particular transistor is made, what are the useful things, useful parameters which the designer needs to know. That information is given in the PDK. And PDK is made by the foundries, and their PDK is also made by the IDM. PDK is also made by the EDA tool vendors like Synopsys and all those Cadence people. They also make PDKs. So this is what the PDK contains. It contains data files, it contains models, it contains all those information which are related to the physical layout and what are the design rules, how the physical layout has to be done, how the DRC LVS has to be carried out. So there, PDK also contain different cell libraries. If you have to do a digital design, you need various gates. So the foundry may give around 700, 800 different types of gates, low power, high power, standard VT, high VT, all that. And IO pads, it can also give you the memories, various memory cuts, because normally a designer doesn't have to design a memory. There is some process angle involved in designing memories, not that easy. So better somebody else has designed for you, you better use that memory, embedded memory, SRAM, or various types of DRAM, cache memory, and all that information is there in these design kits. There are various types of, you can say, we call it I will give you an example, like a SCL, we have a 180 nanometer. So there are various process flavor in that. And process flavor in the sense, you can do pure digital, you can do low power digital, you can do RF, you can do analog. For doing a good analog, you need a lot of a suite of resistors, a different type of resistors. Because in a circuit, if there is one resistor whose value is 50 ohm, and there is another resistor whose value is 5K, you cannot use the same film for that, because then the area will be quite large. So you need different type of resistors for that, and which the foundry will give you. So these are some of the names. Gate all around is below 5 nanometer. Back metal, FinFET, you are aware, silicon on insulator. So bulk and all those things are there. So these are the different flavors which are available, and the designer can use any of these technology depending on whatever he wants to design, what the specifications are, provided the foundry is giving him option to use these. So some of these may not be available, like due to some reasons, but these kind of available options are there. Some of these slides I will skip, how to make PDK and all those things, just to give a glimpse of a PDK. Like PDK will have a layer name. What are the technology layers? What is the name of those layers? Normally they are represented in a color code. As you can see, it has a layer number, like it has abbreviation. This represent NVEL, this represent P, this represent poly, this is an active, this is a contact, this is a metal, this is a second metal. So these are the layer and these are the numbers. So all these informations, they are given in a technology file, which are basically used while designing circuits. This is an example. You have designed a layout which has a symbol now. So these symbols, each symbol has a particular name, each symbol has a particular ID. You take that symbol, draw the circuit using your, if you are using a tool, EDA tool, Virtuoso schematic editor. By using that, you can take this and draw a circuit. You can simulate it. And finally, you can, after that, because if this is a transistor, how it has to be laid out, P-cell can tell the different layers in that. And this is how, after the layout, this is how the circuit will look like. And then you can do a simulation. It's basically a band gap reference circuit, and you can simulate, because we are seeing how the band gap reference voltage varies with temperature from 0 to 200-degree temperature, how much variation is there, how it varies. So this is just an example how to use these PDK for making the design. So some of these steps these are some of the steps in the design. I will skip some of these steps, antenna and all that. But finally, I will now, as you are aware, the chips have become very, very complicated because of SOCs and because of low power, because we are putting a lot of transistors, close to more than 5 billion transistors in a small area of, say, 23 by 23 square. So some circuit works at low voltage, some circuits work at 1 volt, some at 800 millivolts, some at 700 millivolts. So there are different voltages in that chip. And when there are different voltages, you should have an LDO, you should have a voltage, you can say you have to give those voltages to the transistors who are working in those voltages. So voltage grids have to be like laid out, have to be designed for different kind of voltages. And so all this multi-voltage domain check becomes more complicated. And but there are tools who will do all these things. Similarly, in a circuit, if you have, this is a chip, there is a mixed signal part and there is a digital part. Each, though it may be using 1 volt VDD, but you cannot have a same grid for both. You have to design a separate grid for both. And from the outside at the pad level, this VDD line, which is a 1 volt of both, that will be shorted. But in the chip, it has to be separate. The same way, if more voltages are there, multiple voltages, because of low power design, you have to design all these grids, voltage grids separately. And then from the outside, you will get only one voltage, say 1.5 volt, and all other things you might have to generate within the chip by using LDOs and things like that. So the design becomes complicated, and multi-voltage, you need a lot of good EDA tools which support that, so that you are able to do this verification, so that there is no short and things, the entire circuit is working fine. Nowadays 3D ICs are there. So when you are stacking these components, when you are stacking the chips on top of each other, and then you also need a lot of other EDA design tools, which so that you are able to verify your design things. Now I will just show you certain pictures related to the process thing, which is this is the design flow. I will skip some of these things. As I told you, the big signal design flow, it involves a lot of various tools, and it's basically a flow. So this is a complete, this requires another, you can say, a lecture by itself, how these designs are done, what are the various tools, and what are the various steps in the design, as you can see by these block diagrams. So this is a vertical stack, and this is a stack of the metal. As you can see, the transistor is here below this. This is the first metal, this is second metal, this is third metal, this is top metal. Top metal is thick. There are various reasons for that, because first of all, we are giving power through the top metal, so a thick line is used. And when we make inductor, we prefer the top metal, because the resistance when the metal is thick will be less, and we can have inductor value more. Normally we can have around 5 to 7 nanohenry inductor within the chip. So this is an example only of 4 metal, but nowadays we have around 8 to 12 metal lines. So these metal lines will be stacked. Here example is of 4, it can be 8. Now the question is here, though the color is same between the two metal, which we call it ILD, interlayer dielectric. So interlayer dielectric is not same, though here it has been shown same. You can see this color is light yellow, this is light yellow, but this is different. But normally it may be same, it may not be same, due to certain reasons. When we are depositing these dielectric, what kind of dielectric are they, whether it's a undoped silicate glass or it's a fluorinated silicate glass. There are many different types of dielectric available. So that is the decision of the process engineers, which one they are doing and why they are doing. So the point here is you can see the complexity involved in making these kind of structures. And this is the back-end flow. And the transistor has been made, which is just below this red line, poly line. And it's on the top of that. Because the transistor is basically, if you talk of 45 nanometer, it's just the channel, the area where transistor is made. It requires only 20 to 30 nanometer kind of thing. But if the transistor is here, it's only taking 20 to 30, at the most 30 nanometer of silicon. But if you have 10 metal and you are taking the signals here, it will need around 6 or 7 micron kind of thing. So you have to take this signal of the source, drain, gate on top of it and then bond it so that there is very less parasitics involved, very less resistance involved. Otherwise, making a very fast transistor, but when the pads go out, it becomes slower because of parasitic, it defeats the purpose. So these back-end design is becoming very, very important at a lower node when you reduce the size of the transistor below 65 nanometer. So these things, lot of new materials like metal, how you're using the metal, aluminum, copper, then your via, how you're putting the vias. Vias is when you are connecting two metals from metal 1 to metal 2. So these via you cannot do with copper, you cannot do with aluminum, tungsten or something because there are process related issues related to step coverage. So some of these issues, one or two issues I will tell you in this particular lecture. So you can see these are the different types of resistors which are normally given. So you have a medium ohmic, high ohmic, low ohmic, diffusion resistors, metal resistors, salicylated, non-salicylated, well resistors, poly resistors. Each resistors have 4-5 positive point, 4-5 negative point, and we have to go through the details of each, and so that we can know when these resistors will be used and where it will be used in the design. Some of these resistors are available in 2T and 2 terminal like this, and in a 3 terminal also. Like there is one terminal here. This means it is sitting in a well, this resistor, so that there is no, if the resistor is like that and below there is a, it's sitting just on the substrate. So substrate coupling, substrate noise can affect. But if I have a well here and I have a third terminal, I can put a bias here. Then where to use what. So these type of resistors, these types of BJT devices, capacitors, they are normally available in any technology. A particular typical parameter at 1.8 volt, IDSAT is normally around 600 microampere per micrometer. And this you can see I of is 15 picoampere and IDSAT is this. So you can divide the two. So that will give you I on by I off, which should be close to 10 raised to the power 5 kind of thing. So at 180, we can have a transistor speed of 65 gigahertz. FT is around 65 gigahertz. And inverter delays will be in picoseconds, 27 picoseconds kind of gate delays. And if you use a standard VT, if you use a high VT, then leakage will be less and the delay will be around 29.4 kind of picoseconds. Okay, so this I am showing you some of these designs which we did for ISRO. This is a onboard computer which is used in satellite. It controls the satellite. It is a radiation hardened design. Lot of gates are there, and you can see here. And this is basically a LDO, which is analog circuit. This is an Ajit processor, 64-bit processor, which was designed by IIT Bombay. Professor Madhav Desai, he did the coding and we did the physical layout. And this is around 12 mm in this side and 12.6 in the other side. And these are the different memory cuts. These are the different memory cuts as different SRAM, and we have put the in different locations. Normally, the memory is not put at the different locations so that where it is needed, so that the access time is less, memory is fast, and the power consumed by the memory also will be lower. And this is a NAVIC baseband. ISRO has a NAVIC and the GPS system, which you call it. And this is the baseband circuit for that. This also is around 12 by 12 mm square area. And here also, these kind of, which you are seeing repetitive, these are all memory cuts. These are all memory cuts. So a lot of memory, it's a purely digital circuit. A lot of gates. Gates will be close to more than 20 million gates in this. A lot of memory. So this is another design, which is an analog design. It's a low dropout regulator, LDO. This is a multi-channel. You can see this LDO, this is single LDO, and this is repeated 8 times. So I will quickly go through is again, this is used in the rocket PSLV. When it goes, it's basically a data acquisition system. And this particular is a digital circuit. This is the analog. This is a capacitors bank. These are various transistors, and these are the pads here. And it's basically a radiation hardened circuit, which can be used in a military or any space applications. And again, this is voltage reference and A to D 14-bit pipeline ADC. This particular circuit here, the area is, I think, around 6 by 6.5 mm. Okay, so this is a sigma delta, which is, you can see 3.7 mm by 3.7 mm area. This is the digital circuit, and other area is your analog circuit. These are the decoupling caps. So you can see that how much area is occupied by decoupling caps. This is LDO. This is LDO, because it needs 2 power supplies, and from outside we are getting one and generating in the chip the other power supply which is needed. So this is the biasing circuit, and this is the modulator. It's a second order, so 2 modulators, second order circuit. And so it's a 24-bit sigma delta and 3.7 mm by 3.7 mm. Again, the same circuit, but it is 16 channel. So you can see here 16 channels have been put here, and the size is 8 by 8.5 mm by 8.5 mm. This is the chip which was made, and it is used in a rocket. The goal of this is we had 2 big boards having a weight of around more than 4 kg. So that 4 kg weight was eliminated by just one chip, which is not even 20 grams. So as you know, 1 kg weight reduction in space means you gain by some 10 crore or so. So this is how these VLSI technology is useful in space, where you are able to make these circuits and reduce the hardness kind of thing. So mask fab, where we make the masks, reticle. One reticle dimension is close to, say, 23 mm by 24 mm. In one reticle, there can be many designs, like this is one chip, this is another chip, this is another chip, like this. So you can have many chips in one reticle, and that reticle is printed by a stepper and scanner during the fabrication flow. So these are different reticle. This is another reticle, different types of chips are there. This is another reticle, different type of chips are there in this. Now I will give you an example of a process. I will skip some of these things, and Monte Carlo and all. Okay, so I will give you the example of like in India, we are starting, Tata is going to start one fab. The big question will be which technology, say. So they have decided on, say, 65 nanometer. Now in 65 nanometer node, there are also various flavors. Okay, so there are various flavors and different type of components. You cannot have all that. So you have to start with some baseline process and keep on adding the other you can say process modules. So each process, like in a 65 nanometer, if you ask me the number of steps involved, that will be close to 1,000 steps are involved in that process. and you have to do each step perfectly, efficiently with 100% accuracy. And if there is a problem in one step, it cannot be, you can say, rework in certain steps. In certain steps is not possible, and it will affect your yield. So this is about the so process development is very critical, because you have not only you have to understand the electrical part, you have to understand the device physics, you have to know a little bit of thermodynamics, chemistry, material science, everything you should have a knowledge of all these things. Then only you are able to develop the process. And then the process had to be characterized, model. Then from the process, your model, you have to make test structures. Based on that, you have to extract certain transistor and parameters, different parameters of the transistors. So you have to design those test structures where you are able to extract different design parameters. And then you have to fit those parameters in a curve, because a designer needs a model which is as per H-Spice model or a BSIM model. So you have to fit those curves in models, equations which the designer use for simulation thing, which are given in PDK. Entire fab has to be maintained very clean, very clean environment kind of thing. So class 1 has to be maintained. Uninterrupted supply of various gases, chemicals is required. So let us, because as I told you, there are a number of steps involved in any process. So I will, this is just a, you can say a portion of that is given, where we are doing, first we start with the shallow trench isolation, where we will make the isolation, then we will do the well, then we will do the gate, then source drain extension. So I will take one example to illustrate what are the issues in the process development, and I will illustrate by examples, by showing some pictures, real pictures. So this is a wafer which we have started. As you can see, we have this wafer is argon annealed, and this is a 8-inch wafer at SCL, is our wafer only, real picture, and the thickness is 725 micron. So this wafer, when it is made, you might have studied that Joe-Churski process. There, it has to be a perfect crystalline structure, single crystal 100 orientation. It has to be perfect. There has to be very less impurities, but still there are certain oxygen, hydrogen, 10 raised to the power 11 atoms per centimeter cube are there, and which like it's difficult to eliminate. Then what we do is, this is the top surface. The ICs are made only, I need only very less area, maybe 50 micron, not more than 5-10 micron of that. So I want that has to be, there should not be any impurity in that. So I have made annealed it by an argon. So there are techniques. So I have pushed these impurities down. So you can see that there are some dot and all there, all that is there. So earlier the wafer was like this, and with some annealing technique, I have come here. So I can do it from there. There are various techniques to do this, back side, front side, and things like that, but that is not the point. So I have got a upper surface which is very pure, ultra pure, and crystalline 100 orientation. And then I have to make, like when you construct a house, you will do a boundary wall. So that is the, here each transistor has to be isolated. So we have to do a boundary wall kind of thing, which we call it a shallow trench isolation. It should not, it's a shallow, it should not be very, like too much depth is not required. So there is a structure which I have to make, which is, you can say like this in a wafer. If I say this here from the top, I have to make a structure like this. It is not at 90 degree. It is at inclination, slightly inclined because of leakages and all that, because we have to control VTs, threshold voltage at the edges, and we have to make this, you can say, by etching, and then we have to fill it by a high dense dielectric, and then this will become a wall kind of thing. As you can see, we have to fill it. So this is the step which I am telling you. This is the first step in any technology, whether it's 45, 32 or 24. So we will define areas which are field areas. Field areas means where is no component will be made. Active area where component will be made. In field area, we have a trench, which you can call it a STI or a trench isolation. So like this, we have to make this. So here you can see here, this is this shape, this kind of thing I have to do. Okay, so there has to be a taper angle, and if I cannot do a 90-degree because of some reasons of mechanical, some stresses and some leakages will also be there. If I do it at a particular angle by physics, you can prove that you get a better lower leakages. And in this area, we have to make a VT high, certainly high, because there might be some polyline going over here, and parasitic transistor should not act. So there it has to be at a taper, and that angle is around 76 and things like that. But at the edges here, there is some mechanical stresses, and how near the other stress can be, STI can be. It depends on what kind of stresses, because you have to dig up two trenches. So how this near how these two can be so near, so that the stresses which are there at these edges, if you are able to maintain these within this limit, it is possible you can make it so near. And this width also you would like to be minimized, so that because this area which you are using in shallow trench isolation, it's a field area. You cannot make any component on, but on top of it you can have some inductor, but otherwise you cannot make a resistor transistor here. So we would like to be this width also to be minimized, but there is a limit by which you cannot minimize that. Beyond that, because of the process, you can say the step coverage of that, because finally you have to fill this with a high dense dielectric. You will not be able to fill without voids in that. And there is no software available on all these things. You have to practice various things on the machine and find out what the exact geometry is. Basically, it's a geometry. You have to make a geometry and you have to find out. So you can see, we will discuss these steps. So you can see here, this is the one we did. This is the one. This is a image of a scanning electron microscope. And how we did, first we took the raw wafer. This is the wafer. And I have grown an oxide, silicon oxide, 145 angstrom. You will not be able to see here. Here, there will be a 145 angstrom oxide here, which is grown all over like this, grown all over on the wafer. It's a wet oxidation, 145 angstrom, and on top of oxide, I have deposited a nitride. Like ammonia, this dimension is around 1200, or exactly is 1188 angstrom. This is, I have deposited in a nitride, Si3 and 4, silicon nitride. It's a deposition. Oxide is it's an oxidation. It's here, nitride is a deposition. And then by lithography, I have opened this window here. And in few steps, there will be first here, you can say a photoresist. So that photoresist, after treatment, I have etched the silicon nitride here. I have etched the oxide here, and then I have etched the you can say silicon here, and created this kind of a structure. And now it has to be, when you are doing, you cannot have a wet etching. It has to be a dry etching and plasma etching. And when you have to do at a particular angle, so etching and deposition, they go together. So that process complexity becomes when you have to make this kind of structures. So you can see here, so whenever any process is developed, what we will do is we will make these thousands and lakhs of these. We have to make perfection in making these structures only. This is one process. I have to do etching and make a V stuck groove like this STI. That's all. And I have to make perfection of that. Each should come similarly in a similar manner within a though of course to a particular window within a window. So you can see this is a wafer. So entire wafer will be like this. We are doing these measurements. So this is a profile after doing the etching. Now you see here in this picture, this is that etch which I am doing. This is a transistor. If you are able to see, this is a transistor. In this is a poly. This is a spacer. This is a spacer is also silicon nitride. And you are seeing some different type of color here. Here you are seeing this. This is a basically a silicide, titanium. So we put titanium on top of poly to make it a titanium silicide. So this whole thing is poly, and on top of it we put a titanium or a tungsten to make it a silicide. This is the oxide, and this is your source and drain. This much. So you can see this source and drain. This is known as XJ, junction depth, which is less than 100 nanometer, and this is around 220 nanometer. So this is the junction depth, and I have to make contact with the source. This is the contact, and this is tungsten, which is making a contact here. And you can see here, this is a shining thing is a tungsten. It's making a contact here. So now this is a spacer. Channel length will be between two, like this is source, and similarly here it will be drain. So this is the channel length. Now two transistor, one polyline is this, one polyline is this. Polyline means this one, this line. There will be another transistor here. So what should be the minimum this thing? So minimum this thing, also if I reduce this below 24 nanometer, I cannot have this kind of a structure because I need some space for this also, which is a spacer. I need some space for making contact. I cannot make a very thin contact because then resistance will be very high and I will not be able to fill it with the process. So I need some minimum dimension here. And similarly, the other transistor to double of this. So at 24 nanometer is the red wall, and below which I cannot make this planar transistor. That's why I have to shift to DG FET or tri-FET or whatever. So the industry has shifted to FinFETs, and there are 3 and 4 generations. So below 20 nanometer, you can see this particular structure is not valid. We go to FinFET, and below 7 nanometer, you cannot have that FinFET also. You have to have a gate all around kind of a structure, which only TSMC has mastered that. Okay, so now in this area, you have to study all those stresses also, because basically they are chemicals all. And there are various films. They have to be stable, not at room temperature. They have to be stable at low temperature, because these ICs can see minus 55 at the lower side. On the higher side, they will see around 125, 150 degrees centigrade. So these have to be stable in this huge range. So you see, my idea is, if I make it very thin, I will have a void. Because when I try to fill by a CVD, you might be knowing a chemical vapor deposition process. It is filled here, it's here, and you get a void here. And if this void, it is a reliability problem. Immediately your circuit will work, but I want the IC should have a life of 20 years. So it will, its life will be affected. It will not be that much. So I have seen a STI width 118 nanometer is not doable. But if I make it 650, I am able to fill it. But I am getting so much area is getting wasted. So I will find exact dimension of this width Height, I know. What should be the height? That depend on the junction, this, because this junction is 110 nanometer. So I can have double this, because I have to make a wall between these two transistors. So here there will be a depletion width. So these two transistors, there should not be any leakage between these and between these two transistors. So I can adjust the height, and which is a you can say a optimized height. And similarly, I will optimize the width. This no software will tell this. You have to do it practically on a burn various wafers and do like this. Okay, and so you have to run various now in lithography. You might be knowing what we do is there is a concept of dense versus iso. Printing 2 lines or 3 lines is one thing which we call it iso. Printing thousands of lines is different. Okay, so we will do it both. We will see if these 3 lines are printed as I want, their pitch and their width, then thousand of these lines are I am able to print or not. Okay, so all these things are done, and finally you will have an optimized of a geometry of this particular thing. And then you should have a hinge like this, so that in a wafer you know where this your isolation is. So because in a wafer there will be so many of these isolations in thousands. So how to identify? So this identification is by this. This is the identification mark. This is a, then once you have made this etching, you cannot fill directly with a high dense dielectric, because then if I put directly, if I try to fill, it can come out. The high dense dielectric, it can come out. I cannot fill directly, because there is no compatibility between, because here this red line is a silicon. So there is no compatibility. So what I have to do is I have to grow a thermally grown oxide. So this this thing which you are saying white in color is a thermally grown oxide, and which is close to some 150 nanometer kind of thing. And if you can say this width is close to 300 something, and so I will grow this in a dry oxidation. And because it's an oxide, it will react with oxygen. It will be a thermally grown oxide, and then I can fill this with a dielectric, because then this is a liner. So this is a liner is formed there, and so this is a liner oxide, and active area liner oxide, and dimensions and all those are given, and that's not the point, because I am here. You see, if we see, this process seems to be very like simple. You have to dig a trench and fill it with an oxide. But when you try doing it on a machine, it's not that simple. It's a very, and this is the first step. And though it appears to be very simple, that there's nothing you have to etch and fill it, but when you start doing, then a lot of complexities are involved in this. So similarly, the process goes, and there are so many different steps, and which we will not cover all these steps. I will show you some of these. So you can see here, this is an STI, how beautifully it has come. This is an active area. This region is an active area. So here transistors will be there. And now this high dense oxide is filled by PECV, plasma enhanced CVD. And so now you can see this surface is top C, it's not very plain. So I have to make it planarized. I have to do a chemical mechanical CMP polishing, and so that all this will come like this after this. So I have to, here that image is not there, but it has to be come like this. So the image has to be planarized. There should not be any voids. Like this is a void, there should not be any voids. So during deposition, there should not be any voids in that. And finally, I will do a CMP, and it will be planarized like this, and this thing will be completely made. As this step, like shallow trench isolation, will be made. Now in a process, like this is one example. In a pre-densification, like this is the equipment, at what temperature, what is the H rate, what are the chemicals used, HCl, this is the name of the equipment. Diluted hydrochloric acid is used, 1:200. Temperature is room temperature. What is the H rate, 35 angstrom. For oxide and HCl 03 and megahertz, because it's a, you can say in an etching, it's basically a plasma etching where RF source is used. And so all that information is there. So this is the name of the recipe, diluted hydrochloric acid 35. So like this, each process step has a recipe for that, and that is programmed. All these machines are quite sophisticated, using a lot of software in that, and that is fixed. You have to go, you have to keep on doing the step by step, and finally what you will get is, I will show you some of the transistors. So you can see here, this is first metal, this is the contact, and this is tungsten. And here this metal is aluminium. There's a titanium, titanium nitride, aluminium copper, titanium nitride, titanium. Like it's a stack of 5. And this is tungsten, because I cannot fill these vertical vias by aluminium. It is not possible. I have to use a tungsten only. That is a tungsten plug. So this is the contact. Here I am making a contact. This may be a resistor or maybe whatever, maybe a source or a drain or a gate. So I have to open a contact window and fill it with a tungsten. So like this is, you can see very neatly taken. This is a gate. And on top of gate, as I told you, I will put a titanium or a tungsten silicide. So it, when the titanium reacts with gate, is a poly, it's a polysilicon. So it becomes a titanium silicide, or we call it a silicide. This layer, this is to lower the resistance. There's no other reason. This is to lower the resistance. And the silicide can make very good contact with the tungsten. So this is the tungsten, and it is making contact with the, and other parts I have put it a nitride, silicon nitride, Si3 or Si3N4 or a silicon nitride. It's this layer is silicon nitride. This layer is silicon nitride. This one. This is a spacer, because it's a low drain. You can say here there will be LDD kind of a structure. So that is the spacer this side. So this is how these things are done. Again, this is another example. You can see here. So I have to, this is the metal stack. There is a titanium, there is a titanium nitride, then there is the aluminium copper, again titanium and titanium nitride. So this may be around 650 angstrom total. And this is around 70 to 80 here, 70 to 80 here. So this is how this looks to make this. So you can see here, metal 1, metal 2, metal 3, last metal, and these are vias, via 1, via 2, via 3. So this is how these things will, this is a structure of one SRAM cell, where we have 2 NMOS and 2 PMOS. This is one RF which we made. It's basically a humidity sensor. It's a relative humidity sensor, where we have an oxide, we have a titanium and oxide, then aluminium, aluminium polymide. So you can see here, this is the, basically we have made a capacitor, and there is a polymide. So this polymide is sensitive to humidity. So depending on the humidity, you can measure the value of these capacitance. It will change, because the properties of the polymide will change based on the humidity. And then you are making contact at this also and this also to measure the capacitance of that, which in turns relate to the humidity. So these small sensors, which we call it MEMS sensors, can be made by using these technique. So you can see this is transistors. So this is the gate, this is spacer, oxide, which you will not be able to see here because it's very thin. It's 20 nanometer oxide. This is source or drain like this. This is also source and drain. This is the contact of the source and drain. This is another transistor. This is contact, another contact. This is another contact. This is that isolation. This is that isolation. So it depends on you. Like you can have two transistors in the same well without any isolation, or you can have each transistor in an isolation also. It depends on whatever your requirement is. You can have a separate well for each transistor, or within a well you can have 100 transistors. That depends on you. Okay, so these are some of the again, this also shows the same thing. This is a metal making a contact. This is a dielectric on top of it, and here again there will be another metal. This is a blow up of the same. Now this xj, because I don't want it to be more, I want it to be less, because it will add to parasitics. See your CGS, CGD, because if this is the source, this is the bottom capacitance, this is the sidewall capacitance. So if I make a source like this, so this much area, this much perimeter is more, so my capacitance is more, so transistor becomes slower. So I want it to be very shallow, what we call as a ultra shallow, USJ, ultra shallow junctions. But there is a limit how much shallow I can make, because I have to make a contact also. If I make it too shallow, then this contact will short this whole thing. So there will not be any transistor action. Like here, if this thing goes here, then it is shorted. Your drain is shorted, so there will not be any transistor action. So all these geometries are decided based on your like different trials on the equipment, on the machine. So you get an idea how best geometry you are able to achieve. So these are some of the structures. This is some of the, I will skip some of these things and how it is done and all that. So these, I will skip some of these things. And optical, now this is a machine which is extreme ultraviolet. It's a very big machine, stepper scanner, which is used. I will not go into all this. Now when a new fab comes, what happens is there will be some failures. The yield will be less. The failures in the starting, there are two types. One is a random failure and a systematic failure. So a systematic failure will be more, because they might relate to something. There is some bug in the machine, there is some issue in your chemicals, there is some issue in your design also, there can be some issue. So systematic failures are more. Systematic yield will be very less in the initial phase, which we call it a technology transfer or R&D development. And when a pilot batches are run, the systematic yield is very, very less than the random yield. So when you ramp up the production, then your systematic yield almost becomes very, very high. Your systematic failures are almost eliminated. You only get random failures. And this is that high production area, which we call it a high volume manufacturing certified process. And so in this area, your failure analysis has to be very, very strong. What kind of failures are coming and how to improve the yield. This is again, you may have to fix the design, you may have to fix the process parameters, you may have to fix your recipes. So a lot of variables are there. And unless one understands the complete thing, what is happening, it will be very difficult to fix up the problem. And there are test structures which are put, like this is one example. There are a lot of test structures which are put to verify the reliability of the device. And these test structures, there is a standards, international standards are there. And these structures are put for electromigration, NBTI, high current injection, time dependent dielectric breakdown of MOS as well as of MEM, and then a TDSRAM, technology demonstration memory, SRAM. So that is chosen as a test vehicle. So you will put memories, and this is the basically a map of that, and you will do you can qualify your fab based on that. So metrology plays an important role. As I told you, there may be 1,000 steps, and some steps there are inline metrology. Metrology is two types. Either you are doing seeing the image, or you are making some measurements of the geometry, which may be a vertical dimension or a lateral dimension, electrical parameter or a geometry, or you are talking about what kind of materials, related to materials you are trying. So here, when you go below 20 nanometer, so all these things become too complex. For example, the wafer size is 12 inch. 12 inch is how much? 300 mm. So this is a wafer. So when you are making structures below, now like TSMC is making 5 nanometer with very good yield. But if there is a 20 nanometer particle sitting on a 300 millimeter wafer, you have to find that particle. So this problem is the same as they say, if you have to find small coins between two towns which are 300 kilometer apart. So in a 300 kilometer highway, you have to find few coins, and you know the size of the coin in 300 kilometer, it comes out to the same dimension, 20 nanometer and 300 mm, because nanometer is 10 to the power minus 9, millimeter is 10 to the power minus 3, so 10 to the power 6, 10 to the power 7 kind of thing. So that is the dimension it is coming, and they are able to do it. So you can say how strong, how good the metrology is. So they are able to find a particle and know whether this particle will have an effect on the yield or not. Planarization is very important. So you have to planarize up to accuracy of 10 angstrom. 10 angstrom in the complete wafer, which is 300 mm. So this is similar to like in a 400 millimeter running track, your fitness control, your flatness control is thickness of few papers. So these two things are similar. So that is these are the challenges. That is the reason even Intel is struggling to get a good yield below 10 nanometer. They are unable to get a good yield below 10 nanometer, and they are going to TSMC for all their processors. Then the fab needs huge amount of various gases, chemicals. I will give you an example. There are bulk gases like nitrogen, oxygen, hydrogen, argon, helium. These gases, they are required in bulk, huge capacities. So you should have a nitrogen plant, oxygen plant. They have to be produced there itself. And the specification of these gases is very high. You can see the impurities level, it's in parts per billion, ppb. Oxygen 0.5 ppb. And how to take these gases to the equipment through various tubes, special stainless steel tubes, which do not create any contamination in that while taking that gases. And you have to monitor all these contents, impurity levels. You have to monitor that, because otherwise, if it goes to the tool, it will spoil your tool. Then ultra pure water. Pure water is only H2O. Nothing is there in that. So pure water will have a resistivity of 18.2 megaohm centimeter. So all these specification, again, you can see silica, boron, sodium has to be in parts per billion or parts per trillion. Another thing is the water have to continuously flow in the pipelines at a particular speed, because if it doesn't flow at a particular speed, then it can, in the pipes, there can be algae, fungi, and like that. Whether your production is there or not, water has to continuously flow. So that is why it needs very, very high volume of water. Okay, so there is this is how we are getting water and all those things. But there are various contaminants in the water as shown in there, and what is the purification method is also given. And these are the different purification method, and it's a very, very complicated water plant which generates pure water. there is an osmosis, there are various filters, there's the reverse osmosis, there's the UV thing, there's the polishing. So much of things are involved in this. And around 9-10 different tests are there to check the quality of the water, like TOC analyzer, particle counter, silica analyzer, and sodium analyzer, resistivity meter, TDS, total hardness by titration. So all these things are done to make sure that the water is effective. Similarly, with the nitrogen has to be, though in the air, a lot of nitrogen is there, which is 78%, but we want a ultra pure nitrogen. So purity level is in parts per million, parts per billion. So we have a nitrogen plant where we store the nitrogen at liquid nitrogen temperature. And this is how the nitrogen plant makes nitrogen from the air. Okay, so this is the nitrogen plant and it is stored in the cryo tank because it's a liquid nitrogen, and then finally how it goes to the plant and things like that. So all these pipes have to be very good. They should not contaminate it. So these are the various gases, then distribution, then there are various acids and alkalis used like hydrochloric acid, hydrofluoric, nitric, phosphoric, then your bases, ammonia hydroxide, potassium hydroxide, then your fluorine, chlorine, all those are used. Then your CVD deposition, silane dichloro, silane tetrachloride, and dichlorosilane, trichlorosilane. So all these things, all these chemicals, your solvents, alcohols, ethylene, acetylene, all these things are used. And you have to maintain in a periodic table around 60-70% of the, more than 70% of the elements are used in making these chips. Huge amount of power is needed. There cannot be any power failure. And your power is requirement is, you can see, around 2 mega MVA, kind of 2 MVA into 3, around 6 or 10 MVA kind of thing. Because we have furnaces which are always maintained at 1200 degrees centigrade, and there are more than 20 furnaces. So huge amount of power is required. Then you have makeup air units, then you have a process cooling water, then you have compressed dry air, process vacuum, process exhaust. So all these things, there are different plants. So there are a variety of thermal systems which are used in a fab, so that making the whole complexity. So different types of manpowers are needed to run this show. Highly skilled technicians, engineers for tool QC, tool operations, various operating the various plants, maintaining fab, maintaining inventory of raw materials of these, handling these gases, chemicals, because some of these gases, chemicals, they are very, very poisonous. Only certified people can handle those gases. They are trained to handle those gases. Anybody cannot handle those. So there is online, then safety systems. There are around 3-4 layers of safety. Even if a small quantity of, even if a molecule leaks, your safety system should be able to tell that and stop that leakage. Then your toxic waste, whatever wastage, highly poisonous waste, how to deal with that. So all these things, they become a, now so some of these process failures, you can see some of these, this is 2 metal lines and some metal is sitting on top of both these and shorting. So this is particularly shorting. So this can result to a failure in the yield. This can result to a failure in the yield. So these kind of failure analysis are done, and I will show you some examples of the now various dies and the layouts. Now each batch, when it comes out, the health of the batch is checked in terms of a process control monitor or a scribe line monitor. There are various parameters. So we are measuring close to 150 parameters. So this shows those parameters. So these are the windows of those parameters, and these are the different types of parameters which we are measuring. And that will tell the health of that batch. And finally, these are various testers and how to test these. I will skip some of these things because the time is over, and I will show you these are different packages. And this is the picture of the die. Earlier we saw the layouts. So this is the actual picture of the die which we have taken from a microscope. This is an SRAM. This is a SRAM memory picture. Memory here. This is LVR. So you can see this is the power grid. This is the power lines. Power grid. This is the power MOS, which is giving 150 milliampere. This is memory. This is LVDS, low voltage differential signaling. So this is VDD VSS lines are going like this. So we have put a structure like this at the corners. This is because of stresses. Because when I cut the wafer, the dicer will run like this. It will run like this. So there at this corner, there may be some stresses developed. So this structure will make sure that it will bear all those stresses, and the die, it will not hurt the die, and this distance has to be kept so that this die is intact. So all these issues are there, and again, this is another chip, this is another chip. So this is a wafer, 8-inch, and this one unit is this. So this is how it is done, and this is a package device which we see inside. This is a chip, and there are different types of packages available. This is a Vikram processor which controls the rocket, which have been designed, fabricated all at SCL, and we are using that. This is another chip. It's a clock chip which is being used in the space. So this is what I just wanted to give you, elaborate, because each of these area is a quite elaborate area, and it needs own skill set. And so far our manufacturing levels, if you see the volume, we don't have a high volume manufacturing facility. We have only one fab, which is a limited capacity, but maybe in the next few years, some fabs might come, and it can give a lot of opportunity for the people. So with this, I will stop. If you have any questions, please feel free to ask.
Thank you, sir, for your wonderful session. So this is a question answer interaction session. So I would like to request all the participants, if you have any questions, please ask directly, sir, or you can post your message in the chat box, or you raise your hand.
Yes. So just before to say that to audience, I just said that sir has wonderfully explained all the things that we are actually in daily life. We are using the chips in every sector, like mobile, computer, and every gadget. We are using the chips and processors. But how how it was made, that is a really difficult thing and very interesting and fascinating thing. So sir have actually absolutely demonstrate us and explain us each and everything in so precise and so in detail. So we are very overwhelmed that we are used every day, but we do not understand what are the effort and uh, what are the signs behind this.
Yeah.
And
Thank you.
also sir show the architecture of the real chips and the process how they are actually made or developed. And each of steps sir have shown with a real picture, and mentioning that the presently the group has making the chips with a 65 nanometers chip size, and also the fab lab facility, how it was actually, and what are the technique and what are the facilities required to develop one fab lab like this. So these are all are wonderful and very much fascinating to all of us, I think. So uh, thank you sir so much for sharing all the details actually.
Thank you. Thank you, sir. Thank you, sir. And my message to the viewers, to the participants, and if younger students are there, it's a very interesting area. Semiconductor is a very interesting field. Lot of job opportunities, particularly for VLSI designers, process engineers also, and whatever we studied at the undergraduate, postgraduate level. So everything counts, starting from maths, organic chemistry, inorganic chemistry, physics, your circuit theory, material science, transport phenomena, Reynolds number, and all that. Everything, Fourier, Laplace, everything is used in designing and making and fabricating and manufacturing these chips. So that is why these courses are there in the undergraduate and postgraduate level. But it's a very interesting area. As sir told, it's a very exciting field. And you can see how wonderfully these things work. And we are making chips which are at 4 nanometer, 5 nanometer dimensions, which even the body cell is in more than 200 nanometer. Any cell in our body, even a RBC, red blood RBC or white blood corpuscles, that are more than 300 nanometer. So you can say, and one memory cell is at made at 5 nanometer kind of thing. So you can imagine that what kind of revolution it has there. And people are targeting even lower structures. And the type of transistor which we studied, a bipolar to FinFET to gate all around, and then something your quantum dot and quantum transistors and things like that. So a lot of innovations are happening in this area and a lot of good opportunities, particularly in India, because we are government is focusing on manufacturing right now. We are not manufacturing anything, though we are using a lot of these electronic gadgets. So the semiconductor component manufacturing will come up in the next 3, 4, 5 years. So it will be a good opportunity for the students who are studying or who are doing their post graduation or doctoral program also.
And now I request to all the participants, this is the open platform. So if you have any queries, please open your mic and ask the question. Shantanu Mishra, raise your hand, please. Please unmute and please ask your question.
Hello, sir. I'm Dr. Shantanu Mishra calling from Haldia Institute of Technology,
Yeah.
West Bengal. I have a general informative question as the chips which are using now by ISRO, all are manufactured in India or it is manufactured elsewhere and it is utilized in India?
No, no, all are not, very few. In fact, only 12 or 13 number are done in India, made in HCL. Others are imported. They are made, like we are using Texas Instruments, Analog Devices, Intel, and other chips. So majority of the chips we are not developing here. We are buying it from abroad. And
The second question is that everyone talking about the dimensions of that chip, whether it is 64 or 32 or 16 or 8 or so. And somewhere I have read out that currently USA is now making 6 nanometer dimensional chips or microprocessor, whatever it is.
right,
And China is also trying to down its size to 4 nanometer.
right.
Which dimension they are talking about? It's a grain size, or it's a separation between the conductor and the what you call CMOS layer?
Yeah, no, actually, till 24 nanometer, it is the length of the channel, like the
Hmm.
distance between source and drain.
Hmm.
So that is, we call it a channel length. That is the technology. Once below this, below 20 nanometer, so the structure of the dimensions of the source and the contact, when we call it a 5 nanometer, they are not 5 nanometer. They are more than 15 or 16 nanometer kind of thing. So they have named this technology as a 5 nanometer or a 4 nanometer. Structures are not 4 and 5 nanometer. They are more than, they are close, they are between 15 and 20 nanometer. But when you go from 6 nanometer to 4 nanometer, you get advantage not in the area wise maybe same, but you get advantage in the speed, maybe a 15% increase in the speed. Or you
But
get,
simultaneously leakage is also increase, and
yeah,
which
no,
will best.
no, no, no. This otherwise we will not go. No? So you get advantage either in the speed or in the leakages, in the power. Your powers are reduced.
Yes.
So that is how they are doing. Because you see, even 32 nanometer, 24 nanometer technology details are not there in the open. What kind of material they are using, what is the structure, no book, no paper you will find. And this 5, 6 below 10 nanometer, nothing is known. Only very cursory knowledge is known. They have named that 4N, 5N, 6N. So 6 nanometer, 4 nanometer, it is the technology name of that node. That doesn't
Okay.
mean that channel lengths are
They
5
have made it.
nanometer. It's not like that.
Okay. Sir, now in India, how many technically expert peoples present to run a modern state of the art lithography instrument?
Yeah, if you see modern, I think nobody is there. That is
Nobody is there.
basically no, not even a single person, but many people of our people, even our ex-SCL, they're working in US and Singapore and other countries. Malaysia, there are 2, 3 fabs. A lot of Indians are there, but not in India because we don't have a factory here.
Yes.
Our litho is basically DUV, that deep ultraviolet, which is basically a 248 nanometer and 192 nanometer kind of stepper scanner, which people have experienced at SCL. SCL is the only foundry in India. So whatever people they are used to that litho. And 192 deep ultraviolet excimer laser, you can print structure as small as 20 nanometer by various resolution enhancement techniques, by immersion lithography, your optical OPM, optical proximity corrections, OPC, and things like that. So there are a lot of things, and but now we have an EUV, which is made by ASML. That machine costs around $350 million.
Yes.
Very expensive machine. And Intel is using that machine, TSMC is using that machine, and they ASML worked for last 20 years R&D to make that machine. Billions of dollars have been pumped by US government and Intel and TSMC to develop that machine. And
Sir,
US,
huge money is required to
huge
run
money,
a.
yeah.
Yes.
Huge
And
money is required. That is why US has put an embargo that that machine cannot be sold to China. And China
exactly.
is developing their own EUV.
Okay. Thank you, sir. That's it.
I think Bishwajit Kundu also raised his hand.
Yes, sir.
Yeah.
Sir, I have a question. Generally, in case of transistor making, so we use generally titanium and palladium to attach the metal electrode with the substrate. So, as you have shown in your BOL structure, so what is the critical thickness of this maybe titanium and palladium to make this BOL structure?
No, we are making our contact sizes, which we have actually done. That is
Okay.
around 130 nanometer by 130 nanometer kind of
Okay, sir.
structure that we have made, which we have
Okay.
done. But at 65 nanometer, they might be doing around 90 by 90 nanometer. When you
No,
reduce
but
that
sir,
dimension, you know,
but sir, 65 nanometer thickness is the metal thickness?
no. Thickness can be more. It is the you can say the you see there is what I mean. You are saying the contact to the transistor,
Yes,
right?
yes,
Contact to
yes.
the transistor. Then metal line when it goes, that will be the metal width will come. But
Oh,
contact size will be in terms of a squarish shape, which is making a contact. If this
no,
is the
but
source,
sir,
I have
but
to
sir,
make
my
a contact.
question. Yes, sir. But in transistor to make this kind of source drain structure, we have to put some palladium or titanium between the metal as well as substrate. Maybe this is silicon dioxide substrate to attach the
Salicide
metal
you are
electrode.
talking.
Yes.
Salicide you are talking.
Okay, so I am asking what should be the thickness of this titanium and palladium to attach this metal electrode with this substrate.
That is where close to like I have a source drain. Source say the source junction is say 100 nanometer. Then on the source, I will deposit a titanium or a palladium, whatever layer you are saying. It can
Yes,
be
sir.
a tungsten also because it is 100 nanometer junction. So I will deposit at least 10 nanometer of that on top of it.
Okay.
So 10
Okay.
nanometer I will deposit that titanium will react with silicon. It will form a titanium silicide,
Yes,
right?
sir.
It will penetrate
Yes,
and
yes.
that will be so 10, 20 nanometer, 10% of the thickness. And then you can put your tungsten, your contact tungsten plug on top of it to make
But
a
sir, okay, but sir, if we put the 10 nanometer of this titanium and palladium, is it possible that it can affect the current and value for, which we can get from this BL structure?
No, no, no. This is only this is put because directly I cannot put a tungsten on a poly. I cannot put directly.
Yes, sir.
And moreover,
Yes.
my aim is to reduce the contact resistance. So
Okay.
salicide and silicide they reduce the contact resistance. That is the only purpose.
Okay. Okay.
So it will not, and so the current it has no role in what generation of current and things like that, and that is a different thing. So here we are reducing the resistance. Contact resistance should be around 2-3 ohms. So we are trying for that. That is the reason we
Okay.
are putting these salicides.
Okay, sir. And another question is, as per your presentation, all the lithography technique uh, has been done through optical lithography or iridium lithography technique?
It's a yeah optical lithography. We are using that excimer lasers are there. It's an optical.
Optical
We are
lithography
using
technique.
optical.
Okay.
Yes, optical excimer lasers having the wavelength 248 nanometer, 193 nanometer, that kind of thing. Extreme EUV is 13.5 nanometer, which is an extreme ultraviolet EUV.
You okay? Extreme
Yeah,
ultraviolet. Okay.
yeah, extreme
Okay.
ultraviolet 13.5 nanometer, which is
So
used to print your 4 nanometer, 5 nanometer kind of thing.
okay. So all the structure have been made by through optical lithography technique actually.
Yeah, 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 yeah. Yes, yes.
Okay. Okay. And another question is,
I don't have the mark set. Yeah, yeah, please.
how this structure, that means how the clean room facility, that means there are some standard of this clean room, so how
Yeah.
this clean room standard affect this kind of BEOL structure, that means regarding
Yeah,
the
it affects.
impurity?
Yeah, it affects. You have to maintain a class one. You cannot go inside that. You can't breathe inside that room where this
Sir,
fabrication, some process is going on. That is true
yes, but sir,
because you,
to make this kind of structure, class that means what should be the class, that means class 1000 or class
class one.
100?
No, no, one. Class one.
Okay, okay, class
Class
1
one.
structure. Okay.
Yeah, even at 180 nanometer, we need class one. Even if
Okay.
the all these Intel TSMC fab, they're fully automatic. Nobody is inside that. So material goes from one station to another through robotic arms and conveyor belts. So there's nobody inside that. So this has to be class one.
Okay, okay. Thank you, sir. Thank you very much.
Uh, thank, thank you so much, sir. And if, if anybody goes have any query, uh, Soma madam, no. Okay. Sir, one question from my side. That today we are in research laboratory. We are using many 2D transistor or 2D devices with based on this 2D material. So, is there any technical facility or the chip industry actually working on this
Yeah,
on this
lot of
2D material based?
lot of people are working on 2D, particularly graphene and other material. There are more than 80, 90 2D material people have synthesized. And a lot of, but not in India, I think, at various labs and IMEC
Hmm.
is there, which are working. IMEC in your Belgium, IMEC. It's a very famous university, as well as they have an R&D center. But in India, not many people are doing, because we don't have that kind of facilities to synthesize those materials, no? To very good material 2D. It will be very difficult for you to synthesize in your lab, because you don't have any full-fledged center for that, and you don't have metrology tool also. Whatever we have synthesized, how to verify that, the various parameters. So to characterize that material also, we don't have that kind of equipment, because this is expensive, but a lot of people are working. But in the next 10 years, the CMOS, whatever transistors we are making, ICs are being made, next 20 years, this will keep on, nobody can replace, because the cost, it's very cheap. As you can see how cheap is your mobile phone and laptop.
Yeah.
And so any technology to be viable, that commercial content is also there. So these things are okay. These a lot of innovations are coming, and in 2D material, they have, you can have you can, because it's basically band gap engineering. You can tune the band gap. You can have lot of different functionalities using those. You can have direct band gap, indirect band gap, and a lot of functionality. Very high speed transistor going beyond 50 gigahertz kind of thing. But that is for future. Maybe after 10-15 years, we can expect some products made from using 2D materials. But right now in India, if you see, not much work is going on in, so that we are able to develop some application out of it. Even abroad also, nobody has made any even a simple gate from 2D material.
Yeah. And one last question, that what about the in-memory computation? Because we are whatever actually working that von Neumann architecture, the processor and memory to a separated unit, and we are actually make the device with that. But nowadays another technology, that is the in-memory computation is arises. So
Yeah, cache
if you
memory, you are able to, by using CMOS, you are able to make very fast cache memories. You are able to make SRAMs, dynamic RAMs, and logic on the same substrate. So embedded memories, embedded processor, because where processor, there is an algorithm, ALU is there. It needs a scratch pad, it needs some memory. So memory is sitting close to that, which is a cache. So cache very fast memories at very low powered memories is possible. And there are a lot of innovative techniques in the memory, MRAM, DRAM. You might have seen that a lot of things are happening. But the thing is, we have to do logic and memory together, sitting very close to each other on the same substrate. That is possible only in case of SRAMs, where you can have logic, analog, RF, memory together in a single piece. Whereas magnetic you cannot have. Then that's why people are targeting of making your 3D stacking. You can say SIP, system in package. In a package, there can be 3-4 dies. There can be a magnetic memory, MRAM die also. And there can be a logic. There can be an RF, which can be from gallium arsenide. So a lot of innovations in package technology. So we should be able to package these. Like in a memory, like for a mobile, if you take a memory module, it's a very thin. It's not a single chip. There are 2-3 chips, 2-3 dies which are stacked vertically. But it appears as it's a single chip. That is the package innovation. So a lot of work is going on in package. So you are able to integrate various dies in a package, in a very small package. Small package because your speed will be high. If your package is more, your contacts, your interconnects will be more. They will consume power. They will be slower. So there is a disadvantage only. That's why we are stacking two dies like this, so that the interconnections are just making contact on top of each other. The wire lengths are not there. It's minimized. That is the reason. So we get advantage speed, high speed, low power, low area.
thank you, because these discussion are never ending. Actually, it should go very for long time actually.
Yeah.
But due to some time restriction, we need to stop somewhere. But uh, I need to say again, thank you, sir, for giving or accepting this invitation and giving this wonderful lecture and explain in detail to us and every aspect of this semiconductor chip technology.
Thank you.
So,
Thank you, sir.
and now this is a small time to give a small token of appreciation for as a digital memento. So I am trying to share my screen. So sir, if you kindly stop your presentation, so I can present my.
I think okay, sir.
Okay, just a few minutes, sir. So small token of appreciation, a digital memento. Please accept this from our side for your wonderful lecture.
Okay, thank you. Thank you, sir. Thank you.
And thank you to all the participants also for your engagement and this wonderful interactive session. And I now over to our HOD Dr. Dipankar Das sir to say and conclude the session.
Okay, thank you, Dr. Vishwajit Das, for sharing this digital memento for a small token of appreciation from Dr. Sudhir Chandrasur, Institute of Technology and Sports Complex, JIS Group. Thank you, sir, for your valuable speech, and thank you all the participants for attending this 6-day online AICT sponsored ATAL FDP. So thank you, sir. A good night.
Thank you. Thank you, sir. Thank you.
Oh, welcome.
And small announcement that okay, this is the end of day 2, and tomorrow we'll entering in day 3, session 5 and session 6, starting from again 6 p.m. So I am again requesting all the participants to stay with us, and your active participation is the success of this program. So again, we already shared the feedback form